Alright, so we're going to start with 8.4. This is the first video of two that we'll have from 8.4. And we're going to talk about improper integrals. Now, until now, we've been finding integrals of continuous functions over closed intervals. That's not going to always be the case when we're doing applied problems. Sometimes we can actually find integrals for functions where the function or the limits are infinite. These are called improper integrals. For example, if we have the integral from 0 to 1 of the square root of 1 plus x over 1 minus x dx, if we look at this, what do we know is going to happen as we get closer and closer and closer to 1? Well, this bottom is going to get closer and closer and closer to 0, while the top gets closer to 2, which means that this inside our square root here is going to go off to infinity. So it's undefined at 1, and it's going to get really, really big, supposedly. We'll look at how that works in a second. But can we still actually calculate the area under this curve? Since x equals 1 is an asymptote, the function actually has no maximum. Can we find the area under an infinitely high curve? Well, here's the thing. We could define this integral as the limit as b approaches 1 from the left side of the integral from 0 to b of the square root of 1 plus x over 1 minus x dx. So in that case, we could take the integral and use a left-hand limit to not let our upper bound be something that's going to make this undefined. And with the limit, we're just going to approach it. We're never actually going to get to the 1 to make the denominator undefined anyway. Now, we must approach the limit from inside the interval, though. We couldn't go in here and say we're going to approach 1 from the outside, because that means you're going to come and approach from the right side of this interval, and that's on the other side of where the thing is undefined. So you've got to approach it from inside the interval. That's why we're approaching it from the left. All right, so then we can actually rationalize the numerator here. And we get this. Because when we multiply, of course, we're going to have the square root of 1 plus x times the square root of 1 plus x, which gives me just 1 plus x, and the square root of 1 minus x times the square root of 1 plus x. We're just multiplying what's inside. So 1 minus x times 1 plus x gives me 1 minus x squared. That is not a perfect square, so do not take the square root of that. So what that gives us then is we can actually split this thing up. That is a single term on the bottom that we can divide into the 1, and we can divide into the x, and we get these two things right here. Now, when we integrate, we can use 1 minus x squared as our u, and when we do our conversions here, we're going to get, this is the inverse sine of x, and over here we're going to get 1/2 u to the negative 1/2 power. Right, so then when we take the antiderivative of that, we're going to end up with u to the 1/2 power. which is the same thing as the square root of 1 minus x squared. All right, and then we're going to evaluate that from 0 to b. So we plug in b everywhere, minus plugging in 0 everywhere. And we still have our limit hanging out here. Well, the inverse sine of 1 is pi over 2. That's not right. Yeah, it is. Sorry. Inverse sine of 1 is pi over 2. That's going to go to 0 as we take the limit. And then the inverse sine of 0 is going to be 0. And we end up with negative square root of 1. So we end up with pi over 2 minus a negative square root of 1, which is giving us a plus 1. So we actually will do our integration, and then after we've plugged our b in everywhere it needs to go, we take the limit. And whatever we get as the answer to that limit is the area under the curve. Now, if that limit goes off to infinity, what do we know? We can't find the area under the curve because it's the infinite limit. It does not approach a finite area under the curve. There will be those that happen that way. So be careful. Now, we say that this integral converges because it approaches a solution. This is not an exact solution because we can't actually be at 1. But this is what the value approaches. This is what the area under that curve from 0 to 1 approaches. That's the value that the area approaches as we add more and more and more and more and more of that area under the curve. All right, so let's do this one. We've got the integral from 0 to 1 of dx over x, and we're going, that's the graph right there. Is this thing going to be, can we actually find the area? So we're going to have to set up a limit, of course, because at 1 this thing's undefined. Sorry, at 0 this thing's undefined. And we're going to approach 0 from inside the interval, so that means we're going to have to approach it from the right side. So we have the limit as b approaches 0 from the right of the integral from b to 1 of 1 over x dx. Now, this is not all that fancy. All we've got to do is take the antiderivative of that, which we know to be natural log of x. And we put in our b and our 1. So we got the natural log of 1 minus the natural log of b, and we do the limit as b is approaching 0. And what do we know? The natural log of 1 is going to be 0. And the natural log of 0 is undefined. We could also write that as this by combining these natural logs into 1. When we do that, we've got 1 over b, and as b approaches 0, this thing's going to go off to infinity, and the natural log will also approach infinity. So that means that the area under this curve from 0 to 1 does not actually approach a set value or a finite value. So this is not one that we can evaluate. And we say that this integral diverges because the area under the curve as we add more and more area does not approach a certain value. It just continues to grow and grow and grow and grow and grow. All right. right, now what's going to happen here is that at 1, we're going to have an undefined lower. We're going to have a 0 on the bottom. So we're going to actually have to split this up into 2 integrals and do 2 different integrals that are both improper. So we have that vertical asymptote at 1. That's going to be our problem. And if we're going from 0 all the way to 3, we're going to have to approach that in this first interval from 0 to 1, and in the second interval from 1 to 3. So we have to split it up into 2. And the improper integrals that we're going to come up with are the limit as b approaches 1 from the left side. As we get closer and closer to 1, we got to approach from inside the interval, remember. From 0 to b of x minus 1 to the negative 2/3 dx. And we're going to add the area that we're going to find as c approaches 1 from the right side, coming in from inside that interval. So we're coming from the right, and that interval is from c to 3. So what we end up with, we end up taking the integral of both of these, or the antiderivative of both of these, and we're going to get 3x minus 1 to the 1/3 of putting in your b and your 0 and subtracting, evaluating your limit, plugging in c and 3, doing your subtraction and plugging in and doing your evaluating your limit. So we get the limit of this. If we have 1, we're going to get 1 minus 1, which is 0. So that one's going to go to 0. We have minus 3 times negative 1 to the 1/3 power. What's the cube root of negative 1? It's negative 1. We end up with 3 there. So out of this one, we're going to have 3. Over here at this one, we have 2 to the 1/3 power. That's the cube root of 2 times 3. This one, as c approaches 1, this is going to be 0, so that goes away. So we're going to end up with 3 plus 3 times the cube root of 2. So the area under this curve over that interval does approach a certain value. Remember, it's not equal to that, but that's going to be what that area under that curve is going to converge to as we get closer and closer and closer on both sides to that actual vertical asymptote. We say that it's equal to it because it converges, and that's what it's going to approach. All right, what about this case? Well, this case we're doing an integral from 1 to infinity of dx over x to the p power, and all we know about p is that p is greater than 0. Now this is leading us toward a test we're going to have in the next part of this section, in the next video we're going to look at, called the p-series test. But anyway, all we know is that p is a positive number. We have no negative numbers there, and we're seeing if the integral from 1 to infinity is going to converge or diverge. Now we can rewrite this as 1 to infinity of x to the negative p dx. And then, of course, we're going to have, since we're going to infinity with our bounds, we're going to have to do the limit because it's an improper integral. Remember, it's not only when we're approaching an asymptote or someplace that makes it undefined, but it's also when this interval goes off to infinity as well. So the limit as b approaches infinity of the integral from 1 to b of x to the negative p dx. All right, so when we do that antiderivative, we're going to increase the p by 1, divide by that number, and we get that. So increase the p by 1. We're dividing by it with that 1 over negative p plus 1, and we have x to the negative p plus 1. And we're evaluating that from 1 to b, and then we'll take the limit. All right, so when we evaluate that from 1 to b, we're going to get b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. Now, as we take the limit, as b goes to infinity, what happens here? Well, if p is less than or equal to 1, then b to the negative p plus 1 is going to get bigger. So the integral will diverge. Now, if b to the negative, if p is greater than 1, then b has a negative exponent, and that means it's going to drop that b to the bottom, and b to the negative p plus 1 would actually go to 0. Therefore, the integral would converge. So that's the difference here. And the whole thing is this right here. If p is greater than 1, or sorry, less than 1, that means that when you add that 1, you're going to have a positive number. When you get that positive number, the b is going to stay on top. If p is greater than 1, like say 2, we have negative 2 plus 1, that automatically is going to drop that b to the bottom. And that means that this would go to 0. But if p is less than or equal to 1, let's say it's 1/2, we have negative 1/2 plus 1. Even the square root of b, as b goes to infinity, is going to go to infinity. So that means this term would go to infinity. This term we know is going to converge for any value of p, because 1 to any power is going to be 1, and the negative p plus 1 on the bottom is just going to either give it a it's going to give it just a number on the bottom. So that's what we're worried about, is this part right here. But that's where our p-series test comes in, and we'll learn more about that when we talk about our convergence tests. And that's all for this part of the section.